Good morning, dear students. In this video, we will discuss about the design of functional metal organic frameworks by post-synthetic modification. We have already learned that metal organic frameworks with desired properties can be prepared by applying the concept of reticular chemistry and crystal engineering principles. That is, we can optimize or we can tune the structure and surface or even the pore environment by proper selection of metal nodes and organic linking groups. However, in some cases, this type of bottom-up synthesis of such materials with pre-designed functionalities will be difficult due to the high sensitivity of such metal organic frameworks. Thermal and chemical sensitivity of ligands and high reactivity of certain functional groups and many such issues make it challenging to always achieve the pre-designed product. For example, if we want to maintain a particular functional group on the walls of the cavity or the pore interior, and imagine this ligand is highly reactive. If the initial ligand, the functional group is highly reactive. If the initial ligand contains that functional group, what will happen? This functional group may get coordinated to the metal center, and that particular functional group won't be freely available inside the cavities after the synthesis of such metal organic frameworks. In such situations, we can adopt the post-synthetic modification method. In this way, desired groups, it can be a new ligand, a connector, functional group, or even metal centers. It can be introduced to the already synthesized metal organic framework. This concept will be clear with this example. Imagine if you want to synthesize a metal organic framework as you see here that contains this particular group on the surface, right? So if we start to synthesize it from the ligand, and we are trying initially itself to attach this particular group into this ligand. Imagine we get this product, and if we are trying to add the metal center, we may not get this final product. We may get a different product, okay, or it may not get coordinated. So instead, what we can do is that we can synthesize a metal organic framework based on this original initial ligand by coordinating it with the metal center. So we get a metal organic framework having this structure, and after the synthesis, we can synthetically modify. We can add this group onto the surface of this metal organic framework. This type of synthetic strategy is known as post-synthetic modification. So this product was not available. This functional group was not available by direct synthesis method. However, we could achieve it with post-synthetic method. So the post-synthetic exchange of organic linkers and metal ions is an expanding area of the field, and it opens up possibilities for more complex structures, increased functionality, and greater system control. So this method is highly versatile because to the existing metal organic framework, we can add more functionalities and hence modify or tune its property according to our need. For example, let us imagine let us see this particular metal organic framework. It is MIL101 based on chromium metal, and it contains NH2 groups on the surface. Okay, so we can post-synthetically, so this MOF is already synthesized on our surface. It has NH2, and post-synthetically we can convert this NH2 group into N3, and later we can by quick reaction we can add maltose groups onto the surface. The addition of maltose group was not initially possible if we start synthesizing this MOF using maltose as ligand. So what we did is, after synthesizing MIL101, we added maltose onto its surface in 2 steps. Okay, so if we get such maltose modified MIL101 using this particular post-synthetically modified MOF, we can sense 33 type of glycopeptides. Okay, so a maltose functionalized metal organic framework MIL101 maltose was developed by a simple 2-step post-synthetic modification process of MIL101 NH2, with the use of this nanomaterial, 33 different types of glycopeptides were detected from the digest of human immunoglobulin G. So, just by a simple process of postsynthetic modification, we could make use of MIN101 for sensing applications and for sensing 33 types of glycopeptides. And now let us see how can we perform this postsynthetic modification, which all ways we can perform it. So, it can be by a ligand exchange process. So, postsynthetic modification techniques can be used to exchange an existing organic linking group in a prefabricated MOF with a new linker by ligand exchange or partial ligand exchange. Okay, so what you see here is an already synthesized metal organic framework, and here these violet or blue ones are metal centers or nodes, and what you see in yellow color are ligands. Okay. So, after the synthesis of MOF, if we need another ligand, a new ligand, we can convert all the ligands by the new ligands. We have substituted all these ligands by new ligands. So, either we can, as you see here, we can substitute or replace all the ligands, or maybe if you want, we can change only one ligand here. So, it can be a complete ligand exchange or partial ligand exchange. This exchange allows for the cavities, and in some cases the overall framework of MOF to be tailored for specific purpose. Okay, so if we need a particular MOF with a new ligand here, we can add that new ligand. Okay, so we can use it for that particular purpose. And uses include fine-tuning the material for selective adsorption, gas storage and catalysis, and for many other applications. We have just discussed about sensing application. So, we can post-synthetically modify existing MOFs for different applications. That is a recent focus of research these days. So, another example we can see, this is vapor phase ligand exchange. So, we already have a synthesized metal organic framework here. We can add linkers, one or two linkers or many number depending on the concentration or control of the reaction. We can add linkers into it. If you want to substitute one linker with another one, we can do that. Okay, so this is a zeolitic imidazolic framework. Here what you see are imidazoles. So instead of imidazoles, we can add substituted, right? Iodine substituted or bromine substituted, chlorine substituted. Imidazole rings can be substituted here, or a different type of ligand can be added. Okay. So, in order to perform the ligand exchange method, MOF crystals are initially washed with solvent and then soaked in a solution of the new linker, the new ligand. So, for this exchange process, ligand exchange process, it often requires heat, and it occurs at a time scale of few days. So, we have to immerse the already synthesized MOF and new linker in the solvent for few days. And the post-synthetic ligand exchange also enables the incorporation of functional groups into metal organic framework. So, here we saw the exchange of ligands itself, but instead we can add only functional groups into already existing ligands of the synthesized MOFs. And this post-synthetic modification can be by the exchange of metal centers. If we want to introduce new metal centers, we can introduce it by post-synthetic modification. For example, if we have to perform catalytic activity and we need a Lewis acid metal center inside the MOF, we can substitute existing metal center with a new metal center. Okay. So, post-synthetic modification techniques can also be used to exchange an existing metal ion in a prefabricated already synthesized MOF with a new metal ion by metal ion exchange process. Similar to ligand exchange, post-synthetic metal exchange is performed by washing the MOF crystal followed by soaking the crystal in a new solution that contains a new metal ion. Post-synthetic metal exchange allows for a simple route to the formation of metal organic framework with same framework yet different metal ions. So, we are retaining the framework structure. Actually, it is very difficult to get the metal organic framework structure, right, if you start the synthesis from the initial level. But by post-synthetic modification, by maintaining the framework, we can exchange the metal ion or ligand, or we can introduce new functionality in that. So, post-synthetic modification can be used to expand upon the structure of the morph. As we have already expressed, the structure can be expanded or new modifications can be brought in. Using post-synthetic modification, morphs can be converted from a highly ordered crystalline material towards a heterogeneous porous material. It can also be used for core shell morph preparation. As you can see here the core is CYP67. Then we are trying to add new ligands onto the surface, so there will be competition coordination, and MOF 74 shell is formed outside the CYP67 core. So what we got here is a core shell of cobalt MOF 74 on the surface of CYP67. So such materials can be, this particular material, this core shell material shows the properties of both these metal organic frameworks, so it can be used for different types of applications. Now let us see the advantages of post-synthetic modification. In some cases, MOF nodes has an unsaturated environment, and it is possible to modify this environment using different techniques. If the size of the ligand matches the size of the pore aperture, it is possible to install additional ligands to existing MOF structure. Okay, imagine if our metal organic framework contain an unsaturated metal center inside the cavity, and if you can add a new ligand to it, if the pore cavity is suitable to capture this ligand or taking this ligand inside, this new ligand can be coordinated to the unsaturated metal center. Sometimes metal node can perform an extension and create a bond with cation. So new metal centers can be introduced to the existing metal within the MOF. The spacers possess additional complexing functions, usually donating groups such as hydroxyl, bipyridine or metalloporphyrin. So new functional groups can be added to it. By using this post-synthetic modification method, a wide range of isotopological structures are possible from a single MOF by reacting it as a substrate with a variety of organic reagents. So we can start from a single MOF and we can add different functionality. The same MOF can be converted into different structures, different MOFs, by adding different functional groups or organic reagents into it. The insertion of new pentant groups, hanging groups on or into the MOF allows the modification of its properties by retaining its crystallinity. The framework and crystallinity is maintained, only the property can be modified. The main difficulty with post-synthetic modification is not to distort the structure of the starting material during the process. Okay, so we have to be careful to maintain the framework structure of the original MOF. So the synthetic and post-synthetic conditions should be controlled accordingly. Different routes have been developed to access post-functionalized MOF based on different chemical interactions while keeping the same native structure. These transformations may involve non-covalent interactions, coordinate bond formation or covalent bond formation.